In section 2.2, we're going to start to talk about how we do calculus with the vector valued functions that we were talking about and introduced in the previous section. So recall that a vector valued function was a function like this r of t here, where our input were real numbers and the outputs were actually vectors with some number of components. And we thought about that in our class, typically we're going to have inputs that are single real numbers, but outputs that are vectors, typically with 3 components. And we also saw that it was important to remember how we thought about the curves in space that this sort of a graph would create, or that this sort of a function would create. The idea, again, was that we think about plugging in a value of t, which will represent some particular spot that's going to be kind of like imagined along the curve. That is, this is like a time where I'm imagining I'm arriving at a particular point. The function then produces a vector, like this vector right here. And that vector is thought of as kind of pointing to the point that's on the line at that particular time, or on the curve at that particular time. And so understanding again that these curves are kind of created by vectors that shoot out individual points is really, really crucial. If we're going to start to do calculus with these sorts of functions, then the first thing that we're going to have to try to define is the main root idea throughout all of Calculus 1. What is a limit? Right? So how am I going to calculate a limit of one of these functions? And what does that mean? Well, let's take a look here at this definition to understand a little bit about how we calculate limits for vector functions. Okay, let r of t be a vector valued function that's defined for all values of t within some open interval containing the number a. A is going to be the value of t that we're moving towards. So we need to make sure that our curve is kind of all connected and stuff like that, and defined as we approach that particular value. Okay. What we're going to write then is the following set of notation, and be careful to note here what is being bolded, because that indicates a vector. So notice here that I'm taking the limit of my r of t function as t, that input value is approaching a, and the output is L, my limit, but it's bolded. The output here is a vector. And I'll know that that limit is the correct limit as long as I can say that the limit here of the norm of this vector subtraction is the 0 vector. Okay, that kind of seems really confusing at first, but before we get into some of the details there, just keep in mind again, we're doing the limit of a vector function, and the output of that was again another vector. Okay, it was a vector that popped out. Okay, let's try to understand though a little bit more about what's happening here with this weird subtraction and kind of visually what it means to have the limit of a vector function. So take a look down here. You'll see that I have this blue curve that's listed down here. And you can see that I can imagine that, again, my r of t is creating points on the graph by going ahead and shooting out individual points via vectors. So maybe I get over here, maybe say when like t is equal to 0 or something, right? When I plug in 0, I get this point. But if I was going to start to do a limit, I might want to figure out what happens as I start to move t towards maybe say the value of a. Maybe that's over here. And so I could kind of imagine that as I move t, I'm going to be thinking about different points on the way to this final point over here. And so that would mean that I'm imagining all the kind of intermediate pink or purple vectors here that are going to be shooting out points along the curve. And so L, my answer to the limit, is this final vector that spits out that final point. And I'll know that I have the final vector because what should be happening elsewhere on the graph is that I should have these two endpoints also form a vector. And if my starting vector that's kind of moving is actually going to slowly, as t changes, turn into this vector of L, then the gap between those vectors should shrink to 0. Notice that this red vector that I drew in here actually is the vector r of t minus L. And you can easily see that again by noting that if we do a vector addition of my vector L and the vector r of t minus L, that is, if I take L plus this stuff, I should just be left with r of t. Okay. So then, of course, that means, if you just rethink about it, if I do r of t minus L, I should be left with exactly this vector. Okay. So as long as this vector here is shrinking down to be the 0 vector, then I know that I have indeed acquired the right limit. So this is kind of a weird concept here. I'm kind of partially thinking about the points that are along the curve, but I'm really thinking about the vectors that are creating those points. What we're going to see in the videos to come is how do we actually then go about computing limits. If I had a vector function, I was asked to compute the limit, what do I actually have to do to make that happen? And then how can I begin to take this concept of limits and extend it to things like derivatives and integrals, like we have seen throughout Calc 1 and Calc 2.